Okay, all right. So it's the end of week 5. We are, I guess after today's lecture, we are officially halfway done with the quarter. And so yeah, that's we're slowly marching through. Okay. Um, and so today's lecture, we will continue talking about Fisher information. We started introducing this on Wednesday, and we didn't get to finish. So I'm going to try to finish that talk here. Okay, and so on Wednesday we just kind of did a quick review of univariate derivatives, and we said that the second derivative of a univariate function gives you information about the curvature, how quickly the function slope changes, and whether it is positive or negative can tell you whether the function is whether the point is a local min or a local max. Okay, and then we expanded this. The concept of a derivative, kind of the multivariate equivalent of the first derivative, would be the gradient, and then the multivariate equivalent of the second derivative would be the Hessian matrix. So so if we take a closer look at the gradient and the Hessian, we can see so here f of w is a multivariate function that outputs a single scalar or single real number, and when you take the gradient of that with respect to a vector w with n components, then it's going to be the vector of partial derivatives. And then when you take basically the gradient, technically the Jacobian of this vector, if you take the gradient with respect to each individual component here, you're going to get another vector of second derivatives, okay, second partial derivatives, and you'll get the columns here, and so this is the Hessian matrix. Okay, a couple properties is that the Hessian matrix is symmetric. Okay, at least I should qualify that and say in most circumstances, where if the second derivative is continuous and exists, then the order in which you differentiate doesn't matter, and so this will be a symmetric matrix. And yeah, if you recall your multivariate calculus terms, the kind of the gradient or the derivatives of a vector will be the Jacobian, and so I guess I got that. Like the second derivative of a univariate function, the sign will tell us whether it is concave up or concave down. You have something similar with the Hessian matrix, and so if the Hessian matrix is positive definite, then the function is concave up, and x is the local min. Okay, and if the Hessian matrix is negative definite, then it's concave down, and x would be a local max. The point at x would be a local max, and if it's both positive and negative, it has both positive and negative eigenvalues, so it's neither positive nor negative definite, then you'll have a saddle point. And then if it's positive semi-definite or negative semi-definite, meaning you got some eigenvalues that are 0, then you need more information to decide if it's concave up or concave down. Okay. Other properties, you can go on Wikipedia and read up on the Hessian matrix, stuff like that. Okay. All right. So the reason why we bother with the Hessian matrix is that it's useful because it tells us about the curvature of the function. And when we apply it to the likelihood or the log likelihood, we can get the idea of the, we can see what the curvature is of the function, and this will tell us how confident we can be in our parameter estimates. Okay, and so what I'm going to do is I'm going to give you an example in the univariate case, and we are going to look at the univariate derivatives, right? Because that's easier. And then once we kind of see it for the univariate derivatives, then we can generalize it to the multivariate case. All right. So the example I have is imagine I've got some kind of bag, some kind of pouch, okay, and I don't have. Okay, so we're going to imagine that there's like marbles inside this pouch, and some of these marbles are red and some are blue. Okay, and the proportion that is red inside the pouch is a fixed value, but it's unknown to us. Okay, and so what I'm going to do is I'm going to draw marbles with replacement. Okay, so so each value I draw, or each observation I draw, will come from a Bernoulli distribution. Okay, and in this example, I'm going to draw 10 marbles with replacement. Okay, and so if I draw 10 marbles with replacement, let's say I observe a red marble 4 times. Okay, so I'm going into the pouch, I look at it, I put it back in the pouch. Okay, I go in and I draw a marble out, and I put it back in. Okay, and so if the proportion of red is theta, okay, then the likelihood function of getting 4 red marbles and 6 blue marbles would be theta to the 4, 1 minus theta raised to the 6. Okay. Okay. If I want to, so this is just going to be the product of a sequence. You know, red, 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 and then not red or blue 6 times. Okay. The overall probability would have a constant, the binomial constant, 10 choose 4 in front of here, but the likelihood function does not care about that constant in the front. Okay, so so this would be kind of the likelihood of some exact sequence of 4 red and blue, 6 blue marbles. You could treat it as one observation from the binomial, and then you would have a kind of the binomial constant in front, but that's not necessary when we're talking about likelihood functions. There's no requirement that it has to add to 1. And if we graph this is the graph that I get. Okay, this is the likelihood function of theta, meaning that as theta varies between 0 and 1, the proportion that is red in the pouch is some mystery value theta. Okay, as that varies from 0 to 1, the likelihood of getting our data, 4 reds out of 10 draws, that's going to also vary. Okay, if the proportion is 0% red, then the likelihood of getting 4 red is 0. Okay, if the proportion is 100% red, then the likelihood of us getting 4 red and 6 blue is also 0. Okay, and if the likelihood is, if the proportion is also something like 0.9 red, okay, if it's 0.9 red, then the proportion probability or likelihood of us getting 4 red and 6 blue is also going to be very close to 0. right? And as the proportion of red in the pouch approaches 0.4, our likelihood will get higher and higher and higher. And so, the maximum likelihood estimate in our case would be 0.4. The likelihood of our data of getting 4 red out of 10 draws is maximized when theta is equal to 0.4. Okay, but it would still be very believable and very plausible if I told you that the proportion in here is not 40% red, but it's, say, 55% red, okay? So there could be a whole bunch of marbles in here, right? Maybe there's 20 marbles and 9 of them, or I'm sorry, not 9, 11 of them are red, okay? If 11 out of 20 are red, then it's 55% red. And it's very plausible for me to draw 10 marbles out of here with replacement and for us to observe 4 of them that are red. Okay, that would still be very plausible for some kind of outcome. Okay, so the maximum likelihood estimate for the proportion that's red, theta being 0.4, we can't be super confident that that is the answer. Okay, so I think that's what I've written on this slide. I've written that the likelihood function shows us that 0.4 is the value of theta with the maximum likelihood. Okay, but it also seems to indicate that 0.5 and 0.3 have high likelihoods for theta as well. Okay, so other values still have high likelihoods as far as what theta could be. All right, now if I do the same thing, okay, but this time I draw 1,000 marbles, okay? I go draw from my pouch 1,000 times with replacement, okay? So this would be very tedious, but you can imagine I go in, I look at a marble, I put it back, shake up the pouch, reach in, grab another marble, put it back in, shake it up, and I do this 1,000 times, okay? And if I do this 1,000 times, let's say I observe 400 red marbles, okay? So my observed proportion is still 0.4, and that would still be my maximum likelihood estimate, but I have I can be a lot more confident in this answer, okay? And so this is what the likelihood function looks like, okay? The likelihood function looks like for 0.4 red, okay? So I've got theta raised to the 400 and 1 minus theta raised to the 600. And that's our likelihood. This is, 1,000 draws, 400 red. This is what our likelihood function is, okay? And basically, if out of 1,000 draws, 400 of them are red, then the likelihood that the proportion being 0.6 is almost 0, okay? It's practically 0. Like, if 60% of the marbles in this pouch were red, and I drew marbles out of here 1,000 times, then it's almost impossible for me to get only 400 red, okay? And likewise, if only 30% are red, and I draw marbles out of here 1,000 times, then it's almost impossible for me to get 400 red if only 30% in the pouch are red. And now that I have 400 observations of red and 1,000 draws total, the only values that are plausible, okay, that we would believe for theta would be, values very close to 0.4, values like 0.38 and 0.42, but values much higher than that or much lower than that for theta become highly unlikely and unbelievable for us, right? So so basically, between this graph and this graph, in both cases we've observed 40% red, but over here I have way more observations, and because I've got way more observations, I can be a lot more confident that the proportion that I have is 0.4, whereas over here 0.4 is the maximum likelihood estimate, but we can also say that other other values are highly probable as well. Okay, student asks, is this related to the law of large numbers? The law of large numbers states that as you take more and more observations, it is going to approach your observed probabilities. The empirical probabilities will approach the theoretic probabilities. Okay, and so it's almost like inversely related. It's the law of large numbers says that if theta were 0.4, then the more values you take, the proportion you observe should be, your proportion should be 0.4. Okay, what we're saying is kind of almost the inverse. It's saying if I take a ton of data, we're almost saying like I have more information about what the theoretic, not the theoretic, what the parameters are for this probability distribution. So they are related, but not in like a direct sense. Okay, so so I think this summarizes basically what I said when we had that graph up, which says I write the pointiness, but maybe I should use the word curvature. Okay, the curvature tells us that values that are close to 0.4, like 0.39 and 0.41, have high likelihood, but there's almost zero likelihood that theta is 0.3 or 0.5. Okay, so there's much less variance as far as what theta could be. Okay, so if we look at the second derivative, okay, of these log likelihood functions, this is what we're going to get. Okay, so the likelihood function is for the 10 draws is theta to the 4, 1 minus theta to the 6. The log of that is 4 log theta plus 6 log 1 minus theta. And the first derivative of the log likelihood function is going to be 4 over theta plus 6 over 1 minus theta. And the second derivative is negative 4 over theta squared minus 6 plus negative 6, 1 minus theta squared. Okay. Log likelihood of the likelihood of 1,000 draws basically turns all of my exponents into theta to the 400 and 1 minus theta to the 600. And then if you take the second derivative of that, you're going to get this quantity, negative 400 over theta squared plus negative 600 over 1 minus theta squared. So that's the second derivative of the log likelihood. Okay, so what does that tell us? Okay, well, if you look at this quantity down here is just 100 times bigger than this quantity over here, right? So it's just I've taken this quantity and I've made it, multiplied it by 100. Okay, and if you evaluate the second derivative of the log likelihood at this point, theta equal to 0.4, okay, then you get what you call the observed information. The observed information for 10 draws is negative 41.667, all right, and for the I guess it's technically the negative of this, but and then the 0.4, if you plug in the maximum likelihood estimate of 0.4 into the other likelihood function, the second derivative of this likelihood function, you get something that's 100 times bigger. Okay, 4,166. Okay, and so the likelihood function of this sample has much more curvature. Okay, much more curvature, indicating that we've got more information and we are more confident in our estimate of 0.4 in the second case when I have 1,000 draws. Okay. So the fact that the likelihood function has much more curvature, okay, that the slope changes rapidly in the second graph, means that the data that we have provides a lot more information about the location of theta. Okay, and that makes intuitive sense because 1,000 draws, we have basically 100 times more information about what theta should be than what we did when we had only 10 draws from the pouch, okay? And so, you know, the relationship between the curvature of the likelihood function and the information we have is tied together in what we call the Fisher information, okay? So the Fisher information, okay, is a way for us to measure the information that a random variable can provide about some unknown parameter. So we want to know, what do our observations x tell us about the unknown parameter theta, okay? The formal definition of Fisher information is that it is the variance of the score, and the score is the derivative or the gradient of the log likelihood function, okay? So it's the variance of this, and that's, I guess that's probably what you learned in 100B when you learned Fisher information. What we want to say, okay, is I'm going to kind of use this approach here, right? So we're going to say we've got some random variable x that comes from a probability density function that's defined by some parameter theta, okay? So it's a probability density or probability mass function of x given some parameter theta. And we're going to assume that the log likelihood is twice differentiable with respect to theta, okay? It's the twice differentiable with respect to theta. Then the Fisher information is equal to the negative of the expected value of the second derivative of this log likelihood, okay? So you take the log likelihood of the basically the probability function, okay? And if you take the second derivative of the log likelihood, you know, you'll get this quantity here, the second derivative of the log likelihood. And the Fisher information is negative of the expected value, okay? And the expected value. So, you know, the way we calculate expected values is we take, you know, whatever is inside the expectation and we multiply it by the probability function, right? So the expected value in this case is taken with respect to the random variable defined by the PDF f of x given theta, right? So sometimes when you only have the expectation here, you might be wondering, like, what is the expected value taken with respect to? So it's taken with respect to. So you might see this notation, okay? This notation where I've got a function written down here. The notation with this function down here means it is the expectation where this is basically your PDF or your probability mass function, okay? And so, you know, I didn't write this, but just a quick, maybe it's worth plugging in. Okay, so you know, when we write something like that, when we say we've got the expected value of y, okay, this notation would be basically you've got the expected value and you've got some kind of PDF or PMF of y, right? Of this, and this is going to be the integral of each value of y multiplied by f of y over dy over basically the entire domain of y, right? So that's going to be the expected value, or if y discrete, you got the sum of each value of y times f of y, okay? And if you've got something more complicated, you've got an expectation of some function, g of y. Okay, and if the PMF or PDF of y then so this is going to be the integral of g of y times f of y dy, right? Or the sum of g of y, whatever this function is, times f of y dy. No, there's no dy with the summation. Okay, so that's just a quick review for your expected values. And so, so anyway, the Fisher information is negative of the expected value of the second derivative, okay, taken with respect to the random variable itself, okay. And that's going to be important because when we look at linear regression, it can get a little bit confusing as to what value is our random variable. All right, so if we do this for a single Bernoulli observation, okay, let's do this for a single Bernoulli observation, then what we have is this is our expected, this is the derivatives, okay, so, all right, so here I'm going to say, let's take the second derivative of the log likelihood, okay. So here is the probability function, the likelihood function for our data. Okay, the log of that is going to be log of theta x, log 1 minus theta to the 1 minus x. Because it's the log, it becomes x log theta, 1 minus x times log 1 minus theta. Okay, well, we want the second derivative of this. Okay, so if I take the first derivative, then I'm going to get x over theta, and so the second derivative will be the partial of this with respect to theta, so it's going to be the derivative of x over theta, and the derivative of 1 minus x over 1 minus theta, and the derivative of this thing is going to be negative of x over theta squared, because this is basically x times theta to the negative 1, and so it becomes negative times theta to the negative 2. Same idea right here. And so this is what we have. And so the Fisher information is going to be the negative expectation of this quantity, and the negative expectation of that is going to be the negative kind of gets distributed, and so I get the expectation of x and the expectation of 1 minus x. All right. So what is the expected value of x? Okay, the expected value of a Bernoulli random variable is that unknown parameter theta, right? Is that value theta. So the expected value of x is equal to theta, so the Fisher information will be theta over theta squared, and 1 minus theta over 1 minus theta squared, which simplifies to 1 over theta and 1 over 1 minus theta. And when I combine these, I get the quantity. So you cross multiply, you find the common denominator, and then you combine them, and you're going to get your Fisher information to be 1 over theta times 1 minus theta. All right, maybe I'll pause here, and I just want to make sure everybody's following along. If this is all good with you guys, give me a green check. Otherwise, ask your questions. And let me give you the answer to the first quiz question today is the letter D, D as in dog. That's going to be the first quiz question. D, D as in dog. Okay, about half of you, about half of you just said that you guys are doing okay. I hope the rest of you are okay. Okay, some few more of you are clicking up here. Okay. All right, okay, so now most of you are saying you guys are doing okay. All right, so this is the Fisher information for a single Bernoulli random variable, okay? And Fisher information is additive, okay? So if you have independent observations of X, then the information you have gets added together, okay? And so, so when you take multiple observations of X, with n observations, your Fisher information is going to become n theta times 1 minus theta. Okay, and that aligns with what we observed when we had 10 observations. Our observed Fisher information was 41.67, and with 1,000 observations, it was 100 times that. It was 4,167, basically. Okay. So that that's what we have here. Okay, so we are going to take kind of that understanding of how the second derivative shows us the curvature of the likelihood function. Okay, and we're going to apply that into the multivariate setting. Okay, and so in the multivariate setting, the second derivative is basically the Hessian matrix. Okay. All right. So this is what it looks like. Here we've got so again, assuming if the log likelihood is twice differentiable and that you can get this Hessian matrix, then the Fisher information is the negative expected value of the matrix of second derivatives of the log likelihood. Okay, so you've got some function x, or you've got some random variable defined by this PDF x, where theta is the given parameters, and then you've got the basically the log of this function, and you want the second derivative of that, and we're going to take the negative expected value, okay, with respect to that variable x, and this is going to form a matrix, and this will be our Fisher information matrix, the information we have about the unknown parameter theta. Okay, so we're going to apply this to our linear regression problem. Okay, so in linear regression, what we're going to do is we're going to do this where we want to learn about the coefficients W. We want to say, what information does our data provide about the coefficients W? Okay, and so keep in mind, so in all of these things, we've been kind of talking about the expected value of x. But for linear regression, x is not the random variable. What's the random variable? The random variable is t. Okay, the random variable is t. That's or y, or whatever you want to say. It's the outcome variable in linear regression. So when we assume that the errors are normally distributed, okay, the probability function that we have for each observation, t sub n, in our generative case is going to be the normal distribution, where the mean is W transpose X and the variance is sigma squared, right? So W transpose X, or if you do it for all of the variables, the big matrix XW, okay, that is the function in the population that that defines the relationship between X and T. Okay, but there's also noise or variance, noise and error, and that noise or error has variance sigma squared. So that is that's what we have. These are the parameters of our well, this is the unknown parameter. X is fixed values. Okay, we're treating X as fixed and sigma squared is fixed. Okay, so so you might see, so if you look at the textbook, you'll have the Fisher information is written as this, okay? It's the negative expected value, okay, with respect to the outcome variable t, okay? Because remember, the outcome variable in our linear regression is t, and it's not x, okay? And we want we want the log of the second derivative of the log likelihood, okay? And so the likelihood is going to be kind of the product of all of this here, okay? And so so this is what we have. So I'm basically applying this, except I'm keeping in mind what my my probability density function is. The probability density function is that each observation t comes from the normal distribution with this mean and this variance, okay? And so so we're going to kind of expand this, okay? So we expand this log likelihood of the linear regression function, and we're going to get this, right? Or the likelihood of this. So the likelihood is basically going to be the product of all of our normal PDFs. And so we saw this back a couple lectures ago. So we have the likelihood of the normal PDF, and so when you apply it for the random variable t sub n for this observation, where the mean or the expected value is W transpose X sub n, and you've got variance sigma squared. This is your normal PDF, okay? And that's the likelihood is the product of all of those things, and so the log likelihood is going to be the sum of all of those things, okay? And just continuing to apply the log likelihood. This is what we get, or the logarithm to the sum. These things are constants, so they just become n log sigma and n log 2 pi, and we keep this intact, right? And okay, and so we want to get the second derivative, okay? And so if you look, so I'm going to just kind of quickly fly through this because we already did the first derivative in lecture 5.1, and so the first derivative with respect of the log likelihood with respect to W. Keep in mind this is like a gradient function, okay? The gradient will be a k/1 vector. It's going to have the same dimensions as W. So I guess back here we're going to assume our matrix X has k columns, okay, and that the vector W is k/1, okay? So the gradient is going to have dimensions k/1, and that's 1 over sigma squared X transpose T minus X transpose XW, okay? And then we are going to take the gradient of this with respect to our unknown parameter W, okay? And when we take the second derivative of this, okay? So this would be like the Jacobian of this basically vector here, or the Hessian of the original log likelihood function with respect to W, okay? The gradient or the partial derivative with respect to W, this quantity drops out to 0, okay? So basically up here I distributed 1 over sigma squared, okay? And so this quantity drops out because that's a constant with respect to W, and then this with respect to W is going to be 1 over sigma squared X transpose X. So this is going to be a k by k Hessian matrix. All right, so this is the Hessian of the log likelihood, okay, matrix of the second derivative, all right? And so the Hessian of the log likelihood is this, and what we want is the Fisher information, okay, which is equal to the negative expected value of this thing, okay? And so remember that when we talk about the expected value here, it is X is not a random variable, okay? So it feels, it feels strange asking what's the expected value of X transpose X, but we are accustomed to seeing X as the as the random variable, but x is not a random variable, right? X is a constant, okay, when we're talking about the, if t is coming from this normal distribution, right? So if t is a random variable, the outcome variable is t, and it's coming from, you know, defined by this PDF. This this thing is a constant, right? So the negative of the expected value here is just going to be this this constant. Okay, so the Fisher information that we have about the parameters w is going to be 1 over sigma squared x transpose x. Okay, let me just pause there. Okay, and just want to check in with you guys again. Let me know if this is going okay or if this was not as good as as the kind of the univariate case. All right. Let me also give you the answer to the second quiz question. Second quiz question is the letter C as in cat. The letter C as in cat is the second quiz question. Okay. So this time a lot fewer people are saying okay as far as how this went. I gotta go slower here. Okay. So the Fisher information here is the negative of the Hessian. Yes, it is the negative. It's the negative expected value of the Hessian. Okay, and it's the Hessian is applied to the log likelihood. So we're taking the Hessian matrix of the log likelihood, and we're asking for the negative expected value. Okay. Is taking the derivative with respect to w the same thing as taking the derivative with respect to w transpose. They're technically different. If you have a scalar function, taking the derivative with respect to w will result in a what do you call it? A gradient with the same shape as w. If you take it with respect to w transpose, then the gradient will be in the shape of w transpose. Okay. The values inside will be the same, but one will be arranged this way in the same shape as w transpose, and then the other will be in this shape where it's in the same shape as w. So there is a slight difference between taking the derivative with respect to w or w transpose. As far as the values inside, the scalar values that go inside that gradient or derivative, the vector of partial derivatives, those values will be the same, but they will be arranged differently. All right. Okay. I don't want us to lose sight of where we are. Remember, so the Fisher information tells us how much information we have about the parameter, the unknown parameter that is part of, that defines our PDF of the random variable. Okay. And so so that's what we have. And it's because the Hessian matrix tells us about the curvature. So if you have a likelihood function with very high curvature, meaning you've got, so you have to think of kind of the multi-variate equivalent of having a sharp peak, right? So in the univariate case, we have this graph indicating less curvature. It's not as there's less curvature in the graph here. It's smoother slopes. Here there's much higher curvature, right? It's a lot more pointy. The slope changes rapidly as we go from this side where it's very positive to over here very negative. It changes very rapidly. Okay, and you have basically something similar going on here with the Hessian matrix, except it's in a higher dimensionality. Okay, so the important thing to remember about the Fisher information is that basically you're taking the Hessian. Okay, you're asking what is the curvature of my log likelihood function? What's the curvature there? And is there high curvature? And if there's high curvature, you're going to have a lot of Fisher information, and if it's a lot smoother, you're going to have less curvature, and you're going to have less Fisher information there. Okay. You know, the whole idea of the negative expectation of the that it's a little bit strange, but just know that it's tied to the curvature of the function. Okay. All right. So just a little bit of interpretation here. Okay. The model of our data is this. All right. And sigma squared is the variance that we have in this noise parameter epsilon. Okay. Right. So this is kind of the true relationship. W is the true relationship between W and for how we go from X to T. Okay. But then we also have noise parameter epsilon. And so if there's lots of noise, sigma squared is large. Okay. And because sigma squared appears in the denominator here, then your Fisher information is small, and you're going to have less confidence in your estimates of W. Okay. On the other hand, if sigma squared is small, the Fisher information is large, and you have more confidence in your estimates of W. So, which just kind of matches intuitive sense in that if the data you have is very noisy, how confident can you be in your slope and intercept estimates versus if your data kind of fits that, has less variance and, you know, almost looks like a line when you plot it, you can be a lot more confident in the slope and intercept. All right, so so that's today's lecture on Fisher information. I think you should have seen some of this a little bit in 100B, and I'm hoping being exposed to it again in this class does not feel crazy overwhelming, or that you'll be able to kind of get your head around the concept the second time around. Okay, we're gonna stop here today, and we will see you guys on Monday. Have a good weekend, and yeah, we'll see you then.